Hello everyone, I am Himanshu Mishra, and in this week we will going to discuss the question from friction. So until now we have discussed the question of equilibrium methods. We have discussed about the virtual work method to solve the problem, and now we proceed to the friction. So basically we will be going through some basics of the friction before we start solving the problem, and then will solve some of the problems of friction. So most of the problems are based on the static friction, and there are a couple of problems which are based on the wages. So before going to the problems, let's revise the basics, very basics concept of the friction. So basically, friction occurs when there is a force exert on the body such that it has the tendency of motion. For example, let's say you have a plane here and you have a body here, and there is a force which is acting normal to the body. Now there is a vertical force which is acting on this block, and we know that the force is not going to create any motion, so body will not move any in the horizontal direction. So there is no impending motion, and therefore there will be no friction force occur when this external force is applied. On the other hand, let's say you have a plane and there is a block and there is a force F which is now act in the horizontal direction. Now when there is a force F, this body starts moving from left to right. There is a motion associated with the external force F, and since there is a motion, then there will be a friction force which will act in the opposite direction of F. So friction happens when there is an external force acts on the body such that it has a tendency to create the motion. Now, basically, there are two kinds of friction. One is static friction, and other is the dynamic friction. So, static friction usually occur when the body is in equilibrium state, and something which hold a body to the ground. It actually happens due to the static friction, and it is measured by coefficient of static friction, which is denoted by μs. Whereas dynamic friction occurs when there is a body which is moving in any of the direction, and it is a contact with some plane or some body or some surface, and while there is a motion, the body will experience a friction, and this is dynamic friction, which is quantified by the coefficient of dynamic friction. So let's say if I make a plot where I put friction in the x-axis and the applied force in the y-axis, and let's say if I exert the force, then how the friction force will change. So for example, this you might have seen in the various textbook and in the literature. So let's say this is the friction force or the maximum friction force Fx here, and this is the point where impending motion starts. So until before this point the body is at rest, and after this point the body is in motion. Now if let's say you keep start applying the force F to the body such that your force F is less than the maximum friction force, then the body will be in equilibrium because your applied force is less than the maximum friction force, therefore the body will not move. So this is actually this region. So you keep increasing the forces until your applied force become equals to the maximum friction force, which actually happen at this point. So at this point the impending motion uh, happen, the body is about to move, and before this point here in this red region the force applied force is less than the maximum friction, which means you can solve the equation, you can actually find the friction force, you can actually determine or analyze the friction in the system by using the equilibrium method. or by using the equilibrium equations that we have seen, because body here in this region the body is not moving at all, and body is at rest, or the body or the system is in equilibrium state. So you can use the equilibrium equations like uh, force balance or the movement balance equation to actually find the friction or analyze the friction force. But after this impending motion, or when the body start moving, what happens that then the friction force can be given by this relation, and here the bodies start moving, and when the bodies start moving, the applied force is actually equal or more than the friction force, and in that case you can actually define the friction force by using this relation. So here the friction is quantified by the dynamic friction mu d, and here the friction is quantified by the static friction mu s. So in most of the problem, we have given the coefficient of friction, and if in the case you have not given the coefficient of friction, just see if in the question whether the body is in equilibrium or not, or if it is in a motion, then you can actually use accordingly the coefficient of friction in case you have given both static and dynamic coefficient of friction. So we will going to solve the first problem based on these concepts. So the first few problems will be very easy, and then we will subsequently move to the little more involved problems, and then we will move to the wedge problems. So most of these problems we are going to use the equilibrium equations to analyze the friction force. So for example, let's consider question number 1. Here we need to determine the minimum horizontal force P required to hold the crate from sliding down the plane. The crate has a mass 50 kg and the coefficient of static friction between the crate and the plate is mu s, which is 0.25. So we have given the coefficient of static friction, which is 0.25, and we need to find the minimum horizontal force which is required to hold this crate. So we want to avoid the motion of this crate, and the whole system is in equilibrium state. So here we need to use the static coefficient of friction, and since the system is in equilibrium state, we have to use here the equilibrium equations. So just remember in the previous tutorials when we were solving the equilibrium systems, the first step is to use a free body diagram and then write down the force equilibrium and moment equilibrium method. The only little difference here is here we need to consider the friction force as well, and we need to assign the friction force, and we just revisited that the friction force is always opposite to the applied force, which actually has a tendency to create the motion. So let's make a free body diagram first. So this is force P, this is 30, and this is weight. And when you remove this force P, what happens is block will go down, right? And hence there will be a friction in the opposite direction, which is Fs. So there will be a friction Fs here, and there will be a normal reaction. This is 30°, and this is where the weight is acting. Now we can take the summation of force. So let me first define my coordinate axis. So this is, sorry, so this is my x and this is my y. Right, so if I do the summation of force in the y direction and equate it to 0 because the system is in equilibrium. So I will have n minus p sine theta. Sine theta because I am actually considering this component of p minus 50, which is the weight. So 50 multiplied 9.81 is the weight, cos 30 equals 0. So this is my equation 1. So as of now we have just written down the equilibrium equation which we were doing from the past weeks, and a similar exercise we can do with the x-axis. So the summation of force in the horizontal direction or in the x direction should be 0 due to equilibrium, and the force will be P cos 30. So here the component I am considering is this component because this is in the x direction. So this is my P cos 30 plus a friction force which is mu n. So this is basically Fs minus weight in the x direction, component of weight in the x direction, which is 50 multiplied 9.81 sine 30, equation number 2. Right, so now you can see that you have two unknowns. You have P and N, which are unknown force, and you have two equations. So you don't need to write down the moment equilibrium equation. You can actually find these two unknowns from these two equations. So from the first equation I can write N equals 59.81 multiply cos 30 plus P sine theta, and then I can substitute this equation in equation number 2. So I will get P cos theta plus mu is 0.25, and n is this expression which is 59.81 cos 30 P sine 30 minus 59.81 sine 30 equals to 0. So we have only unknown is P in this equation. And we will have 0.25 multiplied by 424.78 plus P multiplied by 0.5 plus P cos 30, which is 0.866 P minus 245.25 equal to 0. So here we will get P as 140.3 Newton. So this is what we needed to find. So P is 140.3 Newton, and in case you want to find the normal reaction, you can put the value of P in this expression, or in any of this expression to calculate the N. So just to recap here we have given the force F, and we have given the force P, which is unknown, and we have given the coefficient of friction and weight of this block, and we need to find the maximum horizontal force P such that it avoids the movement of this crate, or it avoids the falling down of this crate. So since the system is in equilibrium, we use the equilibrium equations, and we use the coefficient of static friction here, and we saw that if we write down the force balance equilibrium equation, we will have two unknown into equation, and from this equation we can easily find out the unknown force P. So you can see that the problem is very similar that we have solved in week 1 and week 2, especially in week 2 and in week 3 when we were solving problems for trusses. The only difference, little difference, is in the free body diagram we have a friction force now, which has appeared, and we need to consider this friction force in the while resolving the equation in x and y direction. And just note down the direction of friction. It should be always opposite to the applied force, which has a tendency to create the motion. So here the block would have slipped uh, in the right to left in the downward direction, and therefore the friction force should be in the opposite direction, which is from left to right. So now let's move to the next problem. So the next problem is very similar. Here also we have to use the equilibrium force and moment equations. So here we have given the determine the minimum coefficient of static friction between the uniform 50 kg spool and the wall so that the spool does not slip. So again we want to avoid the slippage of the spool, and we know that the system is again in the equilibrium, and we need to use the equilibrium equations here again. So first, as usual, you have to make the free body diagram. Just assume that this circle is in contact. So we need to avoid the slippage of this spool, which will going to happen in the downward direction, and therefore there will be a friction force which should act here. So this is my point A, and then there will be a normal reaction which will be acting here. Let's say it's NA, and we have given the mass of the pool, which is 50 into 9.81. So this is the weight, and then there's a tension. So there will be a tension which will be acting, So it will be acting at 60 degree from the wall. So these are my forces, and we need to determine the coefficient of friction. So when we do the force balance analysis, of course we will encounter friction force and other forces, and we, from those equilibrium equation, when we write down the friction force in the equilibrium equation, we can actually find the value of coefficient of friction. So let's find the tension first, because this tension is also unknown. So if I take the moment along point A, then let me first define the distance. So this is point 3 and this is 0.6 meter. So the movement will be occur due to the weight mg. It is at distance 0.6 from point A. Then due to this vertical and horizontal component of this tension, so you can actually take point 0.3 as a common. So here you have 2 mg minus t minus 0.866 t equals 0, 2 mg equals 1.866 t. So this is 525 Newton. And if you do the force balance analysis in the x direction, having the coordinate system aligned like this, then you will have force which is the component of this tension T sine 60 and this normal force NA. So here you will get the normal force as T sine 60, and if you do the force balance in the vertical direction or in the y direction and equate it to 0, you will have, you have to consider this friction force, the component of this T, and the weight. Okay, so here you can find mu, and you have already know the expression of Na from the above expression, which is T sine 60. So it will be T cos 60 minus mg plus mu, and is T sine 60. So mu is unknown. So T is 525 Newton that we found from the moment balance analysis. We have found the T, which is 525 Newton. So this quantity is 454.6 mu, and this quantity will be 262.5. So 454.6 mu equal to 228, and mu will be 0.5. So this is the mu you will get from the equilibrium equations. So just to recap here, again we have given the system with a weight and with a friction here, and we need to avoid this spool to get slip off in the vertical direction, and for that we need to find the coefficient of friction mu which avoid this slippage. And since the system is an equilibrium, we have written down the moment and force equilibrium equations to find the unknown. Uh, we have done the force balance analysis in the y direction, and we found that the mu appears in the equation here, and to find the mu we actually need to find this normal force Na, and that we will get from the force balance in the x direction. So this is the usual trick that you need to write down all three equilibrium equation, two force equilibrium equation and the moment equilibrium equation, figure out what are the unknowns are there, and try to calculate the unknowns. So you have a three equations, so the unknown should not be uh, more than 3, it should not go beyond 3. So this is one of the restriction of the equilibrium method that we actually discussed very briefly in the virtual work tutorial. So by using this equilibrium method, we actually find out the coefficient of friction here. And similarly, like in the last question, we can actually find the friction force also, and the normal reaction as well, which is the additional quantities in this equation. So until now we have solved two problems, and both of these problems have we use the same concepts, that is equilibrium equations, to find the unknowns here. So let's solve next question. So here the coefficient of static friction between the 50 kg crate and the ramp is mu s 0.35. The unstretched length of the spring is 0.8 meter, and the spring constant is K 660 Newton per meter. What is the minimum value of x at which the crate can remain stationary on the ramp? So as in the question we have given, there is a crate which is balancing on the spring, and we have given the static friction which is 0.35 between the crate and the surface, and we have given the property of spring which is spring constant, which is 616 Newton per meter, and we have to find the x at which the crate remains stationary, right? So the, here the system is an equilibrium, because if the crate remains stationary, then the system will be in equilibrium, and again we will be using the equilibrium equations here. But here we have given the spring force here, we need to consider the spring force, and the spring force can be given as K multiplied by displacement, right? So there is an unstretched length which is 800 meter. So here delta x is unstretched length minus stretch length ls. So in the question what we have asked, that there is a crate in this position, then it, due to the gravity, what happens, this crate move some distance here, which is x, and this is 800 millimeter, this distance, the earlier distance. Then the crate will move towards left direction, and there is a new position of spring. So this spring also compressed, and this compression distance is x, and at this distance the crate will not go further. It will remain stationary, it will become stationary, and the system become in an equilibrium condition. So at x, system is in equilibrium. So due to the gravity, the crate will move. It will slip on this surface until it reaches the position x. And once it reaches the position x, the system remain in an equilibrium. Or this S here is equivalent of Ls. So I should write here delta x, which is L minus x. So we need to find this x, where the where the box becomes stationary, it will not further move. And which is the what is the quantity which avoid the box to move further? It is actually a friction force. So we have to balance the overall, by using the force balance analysis in the equilibrium, we need to balance the friction force and the other forces. So there is a spring force which is acting, and the spring force can be given as k delta s, and further it can be written as k L minus x. And here x we need to find out. L is the unstretched length, which is 800 meter or 0.8, sorry, 800 millimeter or 0.8 meter. Then let's make a free body diagram. So this is the friction force, sorry, this is the spring force which is acting here, and this is the weight of the crate here, and here is the normal reaction, and here is the friction force which is acting, because crate has a tendency to move from right to left direction, and therefore the friction force should be in the opposite direction, from left to right. And my coordinate system will be looks like this, x, and this is my y direction. So if I do the force balance analysis in the x direction, I have the spring force minus the component of the weight, which is 490.5 sine 50 plus friction force equals 0. And we already know what is spring force, which is k L minus x minus 490.5 sine 50 plus f. F is my mu n equals 0, and mu is already given 0.35. And so here we can see that x and n both are unknown in the equation. So we need one additional equation. Let us do the force balance analysis in the y direction and equate it to 0, because it's system is in an equilibrium. So in the y direction we have the normal force which is acting and the component of weight. So here n minus 490.5, which is weight, cos 50 equal to 0. So from this equation we can actually find n, and once we found n, we can substitute here the value of n to find the unknown x. So your n will be 315.287 Newton. So when you substitute in the above equation, you will get, so K is given 660 Newton per meter. Your L is zero point 0.8 meter minus X minus 490 sine 50, which is, and N is 315 multiplied by 0.35. So here you will get X, which is 0.39 meters. So this is the length of the spring, compressed length of the spring, after which the block will not move and it will remain stationary. So just to recap here, we have given the block and which is supported by the spring here, and we need to find the distance or the compressed length of the spring such that the block stop moving due to the friction force. So what happens that we have given the incline here and there is a spring. It has a it has a unstretched length of 0.8 meters. Now due to gravity, what happens, this block starts sliding down along the plane and it will reach to the new position here. Let's say this is your new position and here it is stopped, and here the new length of the compressed spring is X. So this is your new length of spring, which is X, and X is that distance where the block stop moving, because this spring force is the force due to the spring is also exerted in the opposite direction of friction, or sorry, opposite direction to the gravity. So gravity actually what it's doing, it's moving the block in the left direction, and there is opposite force which is acting in the form of spring force which is acting in the right direction, and it is actually balancing the block. So the length of the spring at that case, in that case, length of the spring is denoted by X when the block stop moving, and we need to find this X. We need to find this compressed length of the spring. So we know that how to define the spring force, which is basically the spring constant multiplied by the change in the length. So change in the length means L minus X. So L is the unstretched length of the spring and X is the stretched length, and which we need to find out. So we have used the, so since the block becomes stationary and the system remains in the equilibrium condition, and we use the equilibrium equation. First we do the force balance analysis in the X direction, and we found there is a two unknown X and N. So we have to write down the another equation. So we do the force balance analysis in the Y direction, and we actually found the value of N. And when we substitute the value of N in the above equation, we can able to find the X here. So here you can see that you do the force balance analysis and you can even able to find the stretch length or the compressed length of the spring. In the earlier question, from the same concept, you actually can able to find the coefficient of friction, and in the first question we actually able to find the normal reaction or the external force just from the same concept, the force equilibrium method. So here the only difference is the spring force which is now coming into the system, and here we need to define the spring force, and just make sure that it should be defined in terms of a delta x, or the distance, or which is delta x can be defined as the unstretched length of the spring minus the stretch length of the spring, and the stretch or the compressed length of the spring that we need to find out. So let's move to the next question. So again, this question is very much similar here. So the question is the coefficient of kinetic friction between the 100 kg box and the inclined surface is 0.35. Determine the tension necessary to pull up the box. So again, the system is in equilibrium, and we are going to use the same concept here. So first, let's make a free body diagram. And you can see that there is a surface, there is a tension force which is acting on this rope. So in this part of the rope, there will be a surface tension T which will be acting, and the same force will be acting in this part also. So here also there will be T, and in this part of the rope again there will be a surface tension force T. So in the whole rope, since in this whole rope the total surface tension will be 3T. So you can actually replace this surface tension force with an equivalent force here. Equivalent force here, which is 3T. And this 3T comes because these ropes are elongated in such a way. Just to recap, here we have a surface tension force which is exerted at this part of the rope, and in this part again there will be a surface tension tension force T, and again in this part we have a tension force T which will be acting. So the overall tension force will be 3T. So this 3T is the equivalent tension force which will be acting here. So here we have a force 3T, right? And since the block is going upward, there will be a friction force which is acting in the opposite direction. So here we have friction force F. Here we have a normal reaction force. And here we have a weight. Right? So this is my free body diagram. So just a small thing that you need to note here in this question, that this equivalent force 3T which is acting, because there is a distribution of a force in this rope. So here here the tension force T which is acting in this part of the rope. In this part it's again T, and in this part again T. So overall an equivalent force will be 3T. So once you figure out the equivalent force here, you just need to do the force balance using the equilibrium equation. So again define the coordinate system. So this is my x and this is my y axis. So along x you have this tension, it's a tension force. I'm keep using the word surface tension, but it should be only a tension, it's not surface tension, it's only a tension force. So in the x direction there will be a tension force, and the component of this weight will be 3T minus 9. So this is 100 kg, 100 multiplied by 9.81 sine 60. And then there is a friction force which is acting, minus F. It can be written as minus mu n equals to 0. Right? So there are two unknowns here. There is one unknown which is the normal reaction force, and another unknown is this tension T. Now if you do the force balance analysis in the y direction, you will have this normal reaction force N and the component of this force W, or weight. So you will have N minus 9.81 multiplied 100 cos 60 equals 0. So you can easily find the n from this expression. So my normal deviation is n, which is 490.5 Newton. When we substitute here, we have 3t minus 981 sine 60 minus mu, which is 0.35 multiplied by 490.5 equals 0. So it is 3t minus 850 minus so on solving this you will get T as 340.5 Newton. So this is the tension force. So it's a very similar problem that we have solved previously. So now let's move to the next problem. So here we have the mass of the bar, which is 4 kg. The coefficient of static friction between the bar and the floor is 0.3. Neglect the friction between the bar and the wall. So if alpha equals 20 degree, what is the magnitude of friction force exerted on the bar by the floor? This is the first part of the problem. And the second part is, what is the maximum angle alpha for which the bar will not slip? So let's make a free body diagram here. So there is a bar here, and there is a friction force which is acting between the floor and the bar, but not wall and the bar. So here there is no friction, but here there is a friction. So now since there is a friction, what happens that this bar will try to topple. So let's say if this is my bar, it will try to do this toppling motion and it will fall down, right? Okay, let me make the diagram more clearer. So this is my rest position, then this will be my knee position, and then it will do this. So it will try to fall like this, right? So this point of the bar is actually moving here in the right direction. So there will be a friction in the left direction. So here the friction force direction is towards left. Here it is FB, this is point B, and let's say this is point A. And since there is a friction force, there will be a normal reaction also, NB. Then we need to consider the weight of the bar, which is 4 kg. And here we have a normal reaction force NA. And it's an angle alpha. And there is no friction force which is acting on point A, because we have given it the question. Neglect the friction between the bar and the wall. Right, so the first part is, we have given the alpha which is 20 degree, and we need to find the friction force, FB. So if I do the force balance analysis in the x direction, and this is my coordinate system, the force balance in the x-axis along the x-axis equated to 0, I have forces like NA and this friction which are acting along the x-axis. So I can write NA minus FB equal to 0. This is my equation 1. Both are unknown force. We don't know what is NA and we also don't know what is the friction force at point B. If I do the force balance analysis along the y direction and equate it to 0, what happens? There will be a weight, and then there will be a normal reaction NB. So NB equals to NB minus mg equals to 0, which is NB equals mg. So NB is m is 4, g is 9.81. NB is 39.24 Newton. Okay, so we found the NB, and to find the FB, still even we use the force balance analysis in the vertical direction, we couldn't able to find unknown reaction Na, because this normal reaction Na acting in the horizontal direction or in the x direction. So then we will use the moment equilibrium equation. So if we take the moment at point B and equate it to 0, so at point B I am taking the moment here. So I will have the weight which is creating the moment. So this distance is 0.1, and this distance then will be 0.5, and this distance, the perpendicular distance that we need to consider from the point of application of force to the point B, it should be 0.5 sine alpha, right? Because this is 0.5. 0.5 sine alpha, and we have given in the first part that alpha is 20 minus NA So now if this is my 1 meter, I can easily find this distance, which is 1 cos alpha. So this is my 1 meter. So I can find distance OA, right? So this is 1. Then my OA will be 1 cos 20. So NA multiplied by 1 cos 20 equals to 0. So here you can see that the only unknown is Na. So we can actually find Na from this equation, and then we can substitute Na in equation 1 to find Fb, which is the unknown friction force. So here it is 7.61 minus 0.939 Na equals 0. So my Na will be 7.14 Newton. So this is my normal reaction at point A. So if I substitute above, if I use the first equation, which is Na minus Fb equals 0, I will get Na equals my friction force at point B. So my friction force at point B is 7.14 Newton. So this is my friction force, which is the unknown. Now you can also calculate the friction force by mu NB, right? So if you calculate the friction force by this, it's a maximum friction force at point B my NB is 39.24 that we found earlier here. So FB will be 11.77 Newton. So this is the maximum friction force. So what happens that we found the friction force by using the equilibrium method, which is 7.14. But when we use this expression, we actually got the maximum friction force FB, which is 11.77 Newton. So what is actually happening is, so there is a bar, okay, and this bar is actually trying to slip due to the gravity, and it is actually exerting the friction force here. Now the maximum friction force is 11.7 Newton. That means if the bars actually exert the force here F, which is more than the 11.77 Newton or more than the maximum friction force, what happens, this bar is actually gets slipped down due to the weight. This bar is actually start slipping here like this. It actually start falling downward. But the friction force we have get, which is 7.14 Newton, which means it has not crossed the maximum friction, and which means the bar remains stationary. So this is the friction force we have got, which is 11.77 Newton, because the force need to overcome this friction force in order to have a motion. So if the force is less than 11.77 Newton, we have seen that if the force is less than this 11.77 Newton, the body will remain in equilibrium position that we have discussed in the beginning of the class, right? And if this force become equals to mu m or equals to the 11.77 Newton, then there will be an impending motion. There will be a motion in the body. The equilibrium of the system will get demolished. There will be no equilibrium at all. The body will start moving because the external force now is equal to the friction force, maximum friction force, which we get from the air. So from the equilibrium equation, we got the friction force 7.14, but we found that when we use this equation, we got little more value of friction, which is the maximum friction force value. So you have to compare the force. You have to actually judge the body whether it is moving or not, whether the impending motion starts or not, based on this value. So in other case, the friction force you need to consider, you need to tell what is the friction force based on this value, because based on when you compare the external force with the friction force, you actually consider the friction force based on this value. Since this value is greater than the friction force which we obtained from the equilibrium equation, we will say that this is the friction force. This is the maximum friction force which is acting, which is 11.7 Newton. Because in order to study whether the system is in equilibrium or not, we need to actually calculate the external force, and we need to compare it with a friction force. And the friction force we need to consider is this one, which is the maximum friction force, which is 11.7 Newton. So here, if until the force is less than 11.7 Newton, any external force, the body will remain in an equilibrium. Once it equals to the maximum friction force, which is 11.7 or even greater than 11.7, there will be a motion, and this body will slip down completely. It will fall down, and the friction FB no longer support this rod in an equilibrium system. So now let's find out the second part. So here we need to find the maximum angle alpha for which the bar will not slip. So again we will be using the equilibrium equation, and we already actually used that. So when we use the equilibrium equation, we will actually arrive to the same equations. So now if we use the moment balance equation around B, I will have the weight multiplied by 0.5, and instead of taking sine 20, I can now take sine alpha minus and A cos alpha. So this is a similar equation here that we have used. We have considered the moment equilibrium equation before, but we actually put alpha equals 20 because in the first part we have given the alpha, but now the alpha is unknown. So now here the unknown force, sorry, unknown quantity is alpha here. So when you calculate alpha, you will get alpha equals 31.0 degree. So this is the alpha, critical alpha, where the body will remain in equilibrium and it will not fall, it will not slip. Right. So this question actually clears a lot of concepts. Like when we actually calculate the friction force using the equilibrium equation, we got some value which is around 7 Newton. And when we use the standard friction equation, which is mu n, this is friction mu n, we actually got the friction force which is 11.7 Newton. So here we need to consider the maximum friction force which is 11.7 Newton, because when you analyze the system, let's say you are analyzing some external force which is acting on the system, then whether the system will remain in equilibrium or not, it depends on the value of this friction force. So if the force is less than this friction force, which is 11.7 Newton, the body will remain in the equilibrium. And the friction force is actually quantified by the static coefficient of friction. But once this force equals mu n or 11.7 Newton or even greater than 11.7 Newton, the system will no longer remain in equilibrium position and start moving. So here you need to consider the maximum friction force. So the maximum friction force is actually obtained by using this relation, which is 11.7 Newton. So let's move to the next question. So here we have given a radius of the 40 kg homogeneous cylinder, which is 0.5 meter. The slanted wall is smooth and the angle alpha is 30. The coefficient of static friction between cylinder and floor is 0.2. What is the largest couple M that can be applied to the cylinder without causing it to slip? So without causing it to slip, this indicates that the system is in equilibrium again, and we need to use the equilibrium equations. So first, as usual, we will make the free body diagram considering the friction force. And this is just a rough schematic. So this is the moment, and this is the weight of the cylinder, and then there is a force P, let's say, which is acting at this contact, it's an angle alpha, and there will be a friction force M. So this movement actually try to rotate the ball, and the ball will move from left to right direction, and therefore the friction force will be opposite. Then there will be a normal force here N. So if you do the force and the Cartesian coordinate is x and y. If you do the force balance analysis in the x direction and equate it to 0, then you have P sine alpha minus F equals 0. So P sine 30 minus F equals 0. So this is equation 1, because we don't know P and F both. So if you do the force balance analysis in the y direction and equate it to 0, then you have component of P, which is P cos alpha. You have weight and you have this normal reaction N. So minus W plus N equals 0. Question 2. And W is mg, which is 40 multiplied by 9.81. And F you can return as mu n. So again, P and N both are unknown quantities. So you have two equations and two unknowns. So from equation 1, so first let's write down the moment equation. So if you take the moment at the center of the cylinder, let's consider this is point O and equated to 0, then the moment will cause due to the external moment M and due to the friction force mu s and r. R is the radius. If it's the distance between the point of application of friction force here and the point O, which is zero point 0.5. So M minus mu is 0.3 now 0.2 and R is 0.15 equals 0. So we need to calculate the moment here. So moment will be given as 0.2 multiplied by 0.15 multiplied by n. So here we need to find n. And to find n, we need to solve equation 1 and 2 together because we have two unknowns here and two equations. So we have to solve both equations simultaneously. So from equation 1, I can write P sin theta so I can write P sin theta as 0.5 P minus F is mu n equals 0. So 0.5 P equals mu, which is 0.2 n. So my n will be 0.5 P divided by 0.2. So this is my expression of n which I got from equation 1. If I put the same equation in equation 2, I will have P cos 20 minus 40 multiply 9.81 plus n, which is 0.5 by 0.2 P equals 0. So here we have one unknown P that we need to find to calculate n. So it's 0.939 P minus 392.4 plus 2.5 P equals 0. So it will be 3.439 P equals 392.4. So my P will be 114.4 Newton. So this is the P. Now you can actually put the value of P here to find n, because we required n to calculate the unknown moment here. So n will be 2.5 P. So we are using this equation, this expression here. You can even substitute in equation 2 or either in equation 1 to calculate the unknown n here. So it will be 286 Newton. So this is the value of n. So my moment will be 0.2 multiplied by 0.15 multiplied by 286. So my moment will be then 8.6 Newton meter. So this is the moment. So again we have done nothing special here. We just make the free body diagram, and we found that if we write down the force equilibrium equation, we have got the two unknowns n and p. And to calculate the moment m, which we can't calculate from the force equilibrium equation, we have to write down the moment equilibrium equation. And we found m, which is equal to 0.2 multiplied by 0.15 multiply n. So first we need to figure out n, so that we can figure out by writing down the force equilibrium equation. So from those force equations, we actually calculate the capital N, and then we substitute in the moment equation to calculate the external moment. So now we will move to the wedge problem. Yeah, so before moving to the wedge problem, we will solve this problem. So the concept is more or less similar to the wedge problem. So what usually happens in the wedge problem, that we have given the number of blocks of different shape like this, and at each surface there will be a friction force which is acting, friction force, normal force, weight of the blocks, and so on. And we need to do the force balance analysis on each block. So what do? We actually separate this system. So first we only consider block 1, and we do the force balance analysis in block 1. Then we only consider this block, which is block 2, and we do the force balance analysis for block 2. And then we again separately takes block 3, and we do the force and moment balance analysis in block 3, and so on. So we actually apply the equilibrium equation on each block separately. This is the usual practice we do when we solve the wedge problems. And here, even though it is not a single problem, we will going to use the same concept, because you can see that there are two different bodies which are coupled by this pin joint B at B. So here we are given the 45 kg disc rest on the surface for which the coefficient of static friction is 0.2. Determine the couple. So here we need to determine the couple. So first we will make the field body diagram. So first we consider only disk. So this is my some roughly looks like a disk here. And from the free body diagram, so here there will be a friction force which is acting here, let's say, which is Fa, and here the normal reaction is Na. Now it is actually connected to a pinch joint at point B, so there will be a reaction horizontal and vertical force that we saw in week 2 and week 3 tutorial when we were solving trusses and equilibrium equations. Also when we solved the beam problems in tutorial 4, week 4. So at the pinch joint, we will have our two normal reaction, that say it's Bx and By. And there will be a weight which is acting at the center of this disk. So if I do the force moment balance analysis, let's say at the center, so I will have, and let's say this is my distance r, because we will require in the moment balance analysis. So I will have By r minus Fa r equals 0. So I can write this as By minus Fa equals 0. So By equals to Fa. So this I got from the moment balance equation. If I do the force balance in the x direction and equate it to 0, I will have this friction force Fa plus this reaction force Bx equals 0. So my Bx equals friction at A, and friction at A will be mu Na. Similarly, By will be given as mu Na, right? But we don't know Na. So we have done the moment balance analysis and the force balance in the x direction, and we got the expression in terms of Na, and we don't know Na. So we will do the force balance analysis in the y direction, and here we consider W, which is 45 multiplied by 9.81, then which is balanced by plus Na minus By equals 0. And we know that By is equals to Na, mu Na. So we can write down minus 4 multiplied by 45, 9.81 plus Na, and By is mu Na. So it's mu, which is 0.2 Na equal to 0. So here we have only one unknown Na here, so we can easily found. So here we have minus 441.45 plus 0.8 Na equal to 0. So Na will be 441.45 divided by 0.8. So it will be 551.8 Newton. So this is my normal reaction at point A. So once I found the normal reaction at point A, I can easily find Bx here and By here, right? Which is equals to mu Na. So my Bx equals to By equals to mu Na. So it will be 110.3625 Newton. So this is my normal reaction. But we want to find this movement m. So now what we do, we consider this rod separately. We will make a free body diagram. So this is the rod, and this is the normal reaction Bx and By. Just note down the sign. For the disc case, the By was downward. Now I am considering the By upward because it's a normal reaction force which is exerted on the rod in the upward direction. There will be a movement here, and here we have a normal reaction at point C, Cx and Cy, because there is a pin joint here also, right? So again, if I do the movement balance analysis, but before that, just note down the distances. So this is 300 millimeter and this is 400 millimeter. So if I do the moment balance analysis at point C and I am assuming counterclockwise as positive, then I have m, then there will be a moment due to By, and this is the perpendicular distance and it's in the clockwise direction, so it's minus By multiplied by 0.3. Then there will be a moment due to Bx, and if it is rotate along C, it will be again in the clockwise direction, so it is minus Bx multiplied by 0.4 equals 0. So By and Bx are equal, and it's 110.36, so it's 110.36, 0.3 plus 0.4 equal to 0. So m is 110.36 multiplied by 0.7, so m is 110.36 multiplied by 0.7, which is 77.25 Newton meter. So just to recap here, we have given the system a disc which is connected to a rod, and there is a movement which is applying at the rod, and we need to find the movement. And we have given the coefficient of friction between the surface of disc and the surface, which is 0.2. So there is a friction force which is acting between the surface and the disc. So what we did, we actually separate the problem. So we separate the disc from the rod. Then we do the we made a free body diagram for the disc alone, and based on the free body diagram we write down the force balance and moment balance equations, and we actually calculate the unknown forces like the reaction forces Bx and By and Na which are acting. Once we got the reaction forces, then we again took the rod as a separate system and we assigned the unknown all the forces here. So as we discussed in the virtual class that when we use the equilibrium method, we need to assign all the forces which are acting on the system. So we have again assigned all the forces Bx and By, which are the reaction force, and which we actually previously found out from the equilibrium equations when we considered the disc alone. So we have more two unknown new forces, two more reaction new forces Cx and Cy. So what we did, we took the moment at point C here. In that way, we don't need to actually consider Cx and Cy because the force due to Cx and Cy will create zero moment at point C. So the moment will be due to the bx and by, and we need to find the unknown moment here. So we use the moment equilibrium equation to calculate the unknown moment. So this concept is actually will be very helpful when we solve the wedge problem. So in the wedge problem, what happens again, we are given multiple boxes, multiple bodies which are either in the contact or they are connected to each other. Like in the previous problem here, the disc and the rod connected to each other, and we take disc separately, do the free body analysis, write down the force and moment equation. Then we consider the rod separately, we draw the free body diagram of a rod alone, and then we do the force and moment balance analysis. We will be using the same concept in the wedge problem here in this question. So instead of connection, this there are three boxes and they are actually contact with each other. So when we do the free body analysis, force balance analysis, or when we made the free body diagram, what we do that we will separate each of this box and we will do the force balance and moment balance analysis separately on each box. So here we need to calculate the unknown force P to lift the 200 kg crate. So this crate has the weight which is 200 kg here, and the friction coefficient of friction at all surface is 0.3. So what happens here? There are three bodies, and we need to uh, consider separately. We need to consider each body separately. So these are the body 1, this is body 2, and this is body 3. So we consider each body separately. We will make the free body diagram here, and then we will do the force and moment balance equation. Then we consider second body, and we do the single force and moment balance equation here by making the free body diagram. This is exactly the same thing we actually did in the last question. So first let's consider body 1. Just 1 minute. So let's consider first body 1, and just to recap here again in case you have missed out, in the wedge problem we have given the multiple bodies which are in which, and they are in contact with each other. So instead of considering the whole system, we actually take each body separately, draw the free body diagram, and then do the force and moment balance analysis. The same thing we have done in the previous question here. You can check out the video of this where we solve this question there. So first here let's consider body 1. So this is my body 1, this is my body 2, and this is my body 3. We need to calculate the unknown force P here. So when we consider body 1, so we have a weight which is acting, which is 200 multiplied by 9.81. Now there is the friction force. Now what happens that you can imagine if there is a force P which is exerting here, this block, this second block will actually move in this direction, right? And it will try to lift the body. Plus this block will move in the left to right direction also, right? So what happens, that above body actually moving in this direction and in the top direction because of this lower body, right? Because if you push this body, if you push body B in the right direction, it will move in the northeast direction. So this will push the body 1, this is my body 1, this will push the body 1 upside as well as at the same time in the west direction. So the motion of the body 1 is in the northwest. So the friction force here is due to the wall here is in downward direction, which is Fa, and here we have a normal reaction force Na. The friction force I can write as mu Na. Similarly, there will be a normal reaction force here, which is Nb, and here the friction force is Fb, which is 0.3 Nb. So this is my free body diagram, and you can see it's all horizontal or vertical force, so you can easily use the force balance analysis. So if you do the force balance analysis in the x direction and equate it to 0, this is your Cartesian coordinate x and y. So FB and ME are in the x direction. So this friction should be in this direction, because this body will move here. Because if you are pushing this block B towards the right hand side, this body will try to move in the right hand side and in the upward direction. So there will be a friction force. Yeah, same. So the movement here, sorry. So as I said before, there will be a movement in the right direction, so the friction will be in the left. So this is the force when you apply the force balance in the x direction. So I can write this as 0.3, which is mu n b minus n equals 0. So both are unknown. If you do the force balance analysis in the y direction, you will have weight as well as friction at A and normal reaction at B. So I can write this as Nb minus mu is 0.3 Na minus weight, which is 200 multiplied by 9.81. So from equation 1 here, you actually get Na equals 0.3 Nb, and you can substitute Na here. So it will be Nb minus 0.3. Na is 0.3 Nb, so it will be 0.3 Nb from the equation 1. This minus 1962 equals 0. So it will be 0.91, Nb equals 1962. So Nb is 1962 divided by 0.91. So you will have 2156 Newton, and your Na is 0.3 Nb from above. So Nb is 2156, so your Na will be 646.813 Newton. So this is your Nb and this is your Na, right? So once you found the normal reaction, now switch to body second, because the same normal reactions like N at point B and B, the same normal reaction will be there at body 2. So after finding the normal reaction, just switch to the body 2 here. So here we found Na was 646 and Nb was 2156. So now let's consider body 2, which is this. So there is a force P which we need to found, and there is a friction force Fb, and there is a normal reaction NB here. So NB we already found, FB we already found. Then there will be a friction force at here, which is, let's say it's C, and this is the normal reaction NC in the vertical direction. This is 15 degree, and this is your friction force FC. Okay, so we already know NB and FB because we already found NB and FB, and the same normal reaction force is there in body too. So you might have observed that, because in the beginning we discussed that we need to consider each body separately and do the free body, first draw the free body diagram and then study the force and movement separately on each body. So why this is uh, happening? Because each body actually connected to each other. I mean, there is a contact surface either by a pin joint, or they are in contact with each other, which means they share the same normal reaction forces. Like in the body one, there was a normal reaction force MB which was acting, and the friction FB which was acting. Now the same reaction force MB is acting on body two, but in the opposite direction. So these bodies are actually sharing the same reaction forces, or same normal forces that you can actually see easily when you draw the free body diagram. And therefore, when you separately consider these bodies, you can actually easily find these normal reaction forces. So when we consider body 1, we actually able to find the normal reaction NB and friction force FB, and we will use the same data which we found out previously. So again we do the force balance analysis for the body 2. So we are just writing the equations. And we do the force balance in Y, then we have NC cos 15 minus NB minus FC sin 15 equals 0. Then here we got NC equals 2427.2 Newton. FC can be written as mu NC. Right, and in the x direction, as we have written down, we have FB, we have component of FC, and we have component of NC. Sorry, this is NC. Right, so we have already found FB, we need to find FP, and FC we can find from this NC. FC can be written as mu NC. So NC we already have, so FP, which is mu NB, NB is 2156 Newton, plus P we need to find, mu is 0.3, this is 0.3, multiply by NC, which is 2427 minus, multiply cos 45 minus 0.3, this is N, 2427 NC multiply by sin 15. So this is, here also it's 15 equals 0. So when you solve this equation, you will get P as, because there is only one unknown in this equation, P, and when you solve this equation, the P will be 1978.3 Newton. So just to recap here, we have given the three bodies here, and we need to find the external force P. So what we do, we separate out the blocks here. We divided the blocks into three, like 1, 2, 3, and we separated out blocks. And first we consider only top block 1. We draw the free body diagram in that block alone, and we use the force and moment balance equation there. So now again we come to the second block, and we saw that the same normal reaction force NB and friction force FB, which are acting on block 2, and using the moment and on block 2 we separately make the free body diagram, and then use the force and moment balance equation. You write down the force and moment balance equation to calculate the unknown force P. So these two blocks have actually shares the common normal reaction force at B, which is NB here. So we can actually this is the reason we can actually separate the blocks, and on each block separately we can actually do the force balance analysis alone. Now we will consider the another question. So here also, so this is a very similar question that we have solved. So instead of 3, now we have only given 2 blocks. So as usual we will follow the concept. First we will uh, consider block A only. So this is my block A. This is the force F which is acting at 30, and we will do the we will draw the free body diagram here and use the force and moments equilibrium equations here. Then there will be a normal reaction force which is acting. Let's say it's P and mu s P. And when we do the same in the block B, we will see that the same normal reaction force will be acting here P, which we already found when we do the force balance analysis or moment balance analysis in block A. Here also N, and here we have friction force mu s N. Here also we have a normal reaction force R, and there will be a friction mu s R, and then there is a weight mg. Here we have a weight mbg. So we do the force balance analysis in block A, then we write down the force and moment balance equation for block A, and we will find the unknown reaction forces like P, R, and so on. Once we found P, we do the force balance analysis in block B. We write down the force equilibrium equation as well as moment equilibrium equation. So when we write down the force equilibrium equation, we saw that P is still there. We already found P from the earlier analysis in block A. Then we can actually find the unknown force. So this is very similar to the previous question that we have solved here. So you can try out this question by your own, and we can actually discuss the same question in the next class. Thank you.